Hello, and we've just talked about atomic mass units and atomic mass. Now, what if we would like to think about this in terms of grams? That's what we're going to talk about today. So let's say I have 26.98 grams of aluminum. How many grams of copper would contain the same number of atoms? Now, this is sort of a segue into this section from yesterday or from the previous section. Recall the principle that for two samples containing different components, aluminum, copper, different components, both samples will contain the same number of components if the ratio of the sample masses is the same as the ratio of the masses of the individual components. So we can set this up as a proportion and look at the ratio of sample masses, 26.98 grams of aluminum to unknown grams of copper. And then the ratio of the masses of the individual components would be the atomic masses, 26.98 atomic mass units, to copper's 63.55 atomic mass units. You can find these if you look on the periodic table. And when we do the calculation, we cross multiply, we find that the grams of copper in this equation would be 63.55. Obviously, you don't even have to cross multiply for this. You can see clearly that this will need to be 63.55 grams. That would give us the same number of atoms as the sample of aluminum. So now let's compare carbon and helium. A sample of 12.01 grams of carbon would contain the same number of atoms as a sample of 4.003 grams of helium. And if you look on the periodic table, you can see that those numbers are the atomic mass units for each of those elements. This brings us to a very important concept, the mole. You've probably heard that and wondered, why are we talking about little creatures in chemistry? Well, the mole in chemistry is a unit of measurement. It is not an organism. 1 mole is defined as 6.022 times 10 to the 23rd units. It could be referring to either atoms, particles, molecules. That is what 1 mole equals. That's the conversion factor. 1 mole of carbon, therefore, would be 6.022 times 10 to the 23rd atoms of carbon. 1 mole of helium is 6.022 times 10 to the 23rd atoms of helium. We have 6.022 times 10 to the 23rd atoms of aluminum in 1 mole of aluminum. And 1 mole of water would be 6.022 times 10 to the 23rd molecules of water. The mole is defined by Avogadro's number. He came up with this number measuring a sample of carbon. He found that a 12.01 gram sample of carbon contains this many carbon atoms. Okay, that is where the Avogadro's number came from. So we know that 12.01 grams of carbon contains 1 mole of atoms. We know that 4.003 grams of helium contains 1 mole of atoms. When you look on the periodic table and you see the atomic mass units for aluminum, it's actually 26.98 atomic mass units, and we know that 26.98 grams of aluminum contains 1 mole of atoms. Molar mass is a term we're going to use a lot. It's the mass of 1 mole of a substance. So, the molar mass of carbon is 12.01 grams. We could say 12.01 grams per 1 mole. It's 12.01 grams of carbon per 1 mole. Molar mass of helium is 4.003 grams per 1 mole of helium. Molar mass of aluminum, 26.98 grams per 1 mole of aluminum. So hopefully I bored you with that a little bit. If you look on the periodic table, you'll see these numbers for their atomic mass units. Their molar mass is all of this as we've just talked about. So it's a really important thing to understand. Let's try some calculations now using these ideas. Calculate the number of moles of aluminum atoms in a 10-gram sample of aluminum. Now you could pause the video and do this on your own and see if you get it right, but I'm going to show you how this works. This is just a little chart I made for you to try and help you understand this better. And hopefully it helps. If it doesn't, we can come up with some other idea to help you understand. But we can always convert grams into the number of moles using the molar mass as our conversion unit. We can also transfer the number of moles, or convert the number of moles into the number of particles by using Avogadro's number. And the conversion unit of 1 mole equals 6.022 times 10 to the 23rd atoms, particles, or molecules. So this is just a way to help you keep track of what it is you're converting from and into. So let's try the first question we asked. Calculate the number of moles of aluminum atoms in a 10.0 gram sample of aluminum. So we'll start with 10.0 grams of aluminum. We have our grams. We'd like to convert into the number of moles. That would be right here. How are we going to do that? Our molar mass will be our conversion unit. Here's our conversion unit. Our molar mass is 1 mole of aluminum is equal to 26.98 grams of aluminum. We get that right off the periodic table. And when our units cancel out here, we end up, grams of aluminum cancels grams of aluminum, and we get 0.371 moles of aluminum. Now, what if we have 0.371 moles of aluminum and we'd like to know the number of aluminum atoms in that sample? Well, we could just take the 0.371 moles of aluminum and multiply by this conversion factor. We know the number of moles. We want to know the number of particles, the number of atoms, particles, molecules. We're going to multiply by this conversion unit, okay? And that would be 6.022 times 10 to the 23rd atoms in 1 mole of aluminum. We have these wonderful little canceling out units there, and we get 2.23 times 10 to the 23rd atoms. You'll notice that I'm limited here by the number of sig figs in that number. I have 3 sig figs here, so I can only have 3 sig figs here. Now, we can also calculate this all in one fell swoop as follows. We can start with the grams. 10 grams of aluminum, multiply by the molar mass conversion unit, multiply by Avogadro's number conversion unit, and we will get the same number, 2.23 times 10 to the 23rd atoms. So you try. Here's the little chart if you need help referring to it. Try these 2 different problems and see if you can get those right. I'll have the answer in the next frame, so go ahead and pause the video. Here are your answers. Hopefully you got those right. We're going to move on, but if you have any questions, you can definitely ask me in class. Here is just something to consider while we're talking about moles and comparing different samples. What if we have 2 different samples that are the same component, helium? I'm going to have helium atoms, and we're going to look at some different concentrations. Here in sample A, we have 1 mole of atoms, we're told. We know that the mass then would be 4.003 grams. We have here in sample B some unknown number of atoms, but when we weigh it, we get a mass of 2.0015 grams. So, how many moles would be in sample B? We know that there would be exactly 1/2 the number of moles here. It would be 1/2 of a mole. So when we're comparing molar amounts of the same component, that is how we can think about those. Now, let's go back to our little chart here, diagram, flow chart, however you want to think about it. If we can convert from grams to moles to number of particles in this way using these conversion units, we can also do the same thing going in reverse, okay? We can convert from the number of particles into the number of moles using the same conversion factor, and from the number of moles into the number of grams using molar mass. And you'll just need to think about which number will be in the numerator and which number is going to be in the denominator as you do the dimensional analysis. So you go ahead and try. Find the grams of sodium in a sample with 4,003 atoms in it. The answer for that problem, I'm going to start with the number of atoms of sodium, 4.003, multiply by the conversion factor with Avogadro's number. We're going to put the number of atoms on the bottom of our fraction and 1 mole on the top. That way, the number of sodium atoms cancels out, And then when we write our next conversion factor, our molar mass, 22.99 grams of sodium in 1 mole of sodium. I got this off of the periodic table. We can then cancel the number of moles of sodium right there. And we come up with 15.28 times 10 to the negative 23rd grams is the only unit left. It makes sense. That's what we wanted. And that's how many grams of sodium there are when we have 4,003 atoms of sodium. Now, what if we want to look at compounds rather than just individual elements? After all, the world is made up of a lot of compounds. So let's calculate the mass of 1 mole of this compound, methane, CH4. 1 mole of methane, here's a little example, carbon in the middle and 4 hydrogens attached to it. 1 mole of methane consists of, if we break it apart, 1 mole of carbon atoms and 4 moles of hydrogen atoms. So we can find the mass of 1 mole of methane by summing the masses of the carbon and hydrogen atoms present. So the mass of 1 mole of carbon is 1 times 12.01 grams. And that's our answer. The mass of our 4 moles of hydrogen in methane would be 4 times 1.008 grams, straight off the periodic table right there, okay? That gives us this number. Now we're going to sum them all up. The mass of 1 mole of methane is 16.04 grams. Remember, we're limited as we add these numbers by the decimal places. This is the limiting number of decimal places. So our sig figs are correct at 16.04 grams. Now, recall molar mass. Remember the definition of molar mass? It's the mass of 1 mole of a substance. In this case, it's the mass of 1 mole of molecules. Our methane molecules have a molar mass of 16.04 grams. That's how we calculate molar mass for a molecule. So you try now. Find the molar mass of sulfur dioxide. Here's the molar mass of sulfur dioxide. Hopefully you remembered from our nomenclature unit that sulfur dioxide is 1 sulfur and 2 oxygens. So hopefully you got that answer correct. Let's move on now. And I just posted our diagram up here. We're going to look at 3 different calculation situations first. We're going to look at calculating the number of moles in a compound when we have its mass. So we're just looking at, we have the grams, we've been given the grams in the problem, and we want to find the number of moles. So for calculating this, when we're talking about molecules, it's just a little bit more complicated because we now have to find the molar mass of the entire molecule rather than just the individual element. First, let's do that. Let's find the molar mass because we need to know the molar mass for our conversion unit. We sum the masses of the individual components in, here's our example. Given a 1.50 gram sample of carbon tetrafluoride, how many moles are in this sample? So we know the number of grams. We now need to find the molar mass. Here's carbon tetrafluoride. Remember, it's a type 3 compound. So that's how we write the compound, the chemical formula. We know that we have 1 mole of carbons there. 1 times 12.01 grams is going to give us the number of grams of carbon. We see that we have 4 moles of fluorine, okay? 4 times 19.00 grams, get that from the periodic table, gives me 76.00 grams of fluorine. If I add those all together, that will give me my molar mass for carbon tetrafluoride. Added together is 88.01 grams. Next, we're going to use that. I now have my conversion unit here, right? My conversion unit to calculate the number of moles in this sample when I'm given the grams. Remember, our grams is 1.50. So we start with 1.50 grams of carbon tetrafluoride. Here's my nice conversion unit that I figured out what it is. It's 1 mole of carbon tetrafluoride to 88.01 grams of it. It's my molar mass. And I get this answer, and I can convert it into a scientific notation format as well, and that is the number of moles of carbon tetrafluoride in the sample. So now what if the problem tells me the number of moles and asks me to calculate the mass? I just go backwards. I go this direction, right? I'm going to use molar mass as my conversion unit again. So for the compound, I have to find out the molar mass first. Here we have potassium oxide, and here's the formula for it that you can figure out because you're so good at nomenclature. You all did really well in that unit. I have 2 moles of potassium, right? There's 2 moles of potassium in potassium oxide. 2 times 39.10 grams gives me this. I have 1 mole of oxygen right here, just 1. So I have 1 times 16 grams. Gives me this number. When I add them together, I get 94.20 grams. That is my molar mass. Okay, I have 94.20 grams per mole of potassium oxide. So we use this molar mass as the conversion unit to then determine the number of grams. And my moles of potassium oxide cancel out, and I'm left with the number of grams. Notice I wrote this number like this because I'm limited by 3 sig figs. It's my limiting number of significant figures, and I'm multiplying. So I get 139, and I just put a decimal point there. I don't have to do that because there's not a 0 here. I just did that to let you know you can do that as well to tell the number of sig figs. I can change this into my scientific notation like this and get 1.39 times 10 squared grams. So the last example, what if I want to calculate the number of molecules of something? Let's say I'm given the number of grams in a sample and I'm asked what are the number of molecules? This will be multiple steps. First, I'm going to have to go from grams to the number of moles. And before I can do that, I need to find the molar mass, right? So I can know my conversion unit. After that, I will need to go from the number of moles to the number of particles using Avogadro's number as a conversion unit. So first, we're going to find the molar mass. And to do that, we have water. 2 moles of hydrogen, give us this. 1 mole of oxygen, give us this. I get my total 18.02 grams per mole. That's the molar mass of water. Next, we use that to find the number of moles and then the number of molecules. So let's start with the grams. I know I have a 10-gram sample of water. Oops. And I just realized it's not carbon tetrafluoride. It should be water. I have 1.50 grams of water. When I multiply by my conversion factor for the molar mass, 1 mole of water is equal to 18.02 grams, right? So then I multiply by this conversion unit. 1 mole of water is equal to 6.022 times 10 to the 23rd molecules of water. And I can get a really nice canceling out. Moles of water cancel out here. Grams of water cancel out there. And I am left with, when I multiply everything out, this many molecules, 1.50 times 6.022 times 10 to the 23rd molecules, and that is divided by 18.02, gives me the number of molecules. I can move the decimal point and transfer that into scientific notation, correct scientific notation, for the number of molecules of water. So you try. How many molecules of sucrose, that is the formula for sucrose, are in a 5.00 gram sample? Go ahead and try that and see if you can get the correct answer on the next frame. So here's the correct answer. 8.80 times 10 to the 21st molecules of sucrose. Realize, just as we went backwards on our diagram, we can also go backwards if given the number of molecules of a compound. You should be able to determine how many grams that would be. It's a 2-step process. So, to show proficiency, I've simply included here what you need to do to show proficiency on this section. You have practice problems in your book. You can make up your own problems and solve them and show me. The things that you need to make sure you're capable of doing. You need to be able to calculate grams to moles and moles to grams. You need to know how to calculate moles to the number of particles and number of particles to moles. Also, grams to the number of particles and number of particles to grams. Again, if you know the number of particles, you should be able to find the number of grams of a particular compound. Make sure you can calculate and tell me what molar mass is. So, if you'd like to do something for advanced proficiency, above and beyond that, you can solve problems that require additional conversion. For example, start with your mass in pounds or in kilograms. That's just an extra step. And it's really not very difficult, but that would show advanced proficiency and that you really understand all of this. So I look forward to seeing you in class and seeing what you know.